one of the basic questions you might have is, okay, suppose somebody emailed me a pattern. They said, hey, check out this really cool pattern. You should try to juggle it. But how many balls do you need? So I just have a set of throws, and I reach over into my bag. How many balls do I need to pull out to be able to juggle it? So that's our goal. Suppose we have a site swap. So in other words, it's a pattern that can be juggled. How can we figure out how many balls are needed to juggle that pattern? All right, and we're going to give two different proofs. And they're going to be very different in flavor, use different underlying ideas, and they're both going to answer the same question. Now you might say, why do we need to prove things more than once? If we prove things once, it's proven, right? And it's true. If you prove something once, it definitely is proven. But oftentimes, if you prove things in different ways, you get different insights. So one way you might say, aha, really clean, really clear, but it doesn't give me much insight into how I can relate things together. Another proof might be more cumbersome, but says, oh, look at all these extra features we have built into it. So there is something nice about having more than one proof. All right, well, let's start with our first proof. And this is going to combine together the idea of a combinatorial proof, so it means we're going to be counting something, and string theory. All right, well, what do I mean by string theory? Well, we're going to go back to our setting where we think of our juggling pattern as going around in a circle. So here we have a pattern, 309525. It is a pattern, it's a valid pattern. And we think about things going around in a circular fashion. Remember, we talked about that. We said we can turn a line into a circle. And we can think about juggling patterns in this way. Now, when we talk about string theory, we're not talking about the really physics like, ooh, look how fancy it is, 8-dimensional knots. No, no, no. Here, we're talking literal string. And what we're going to do is answer the question, how much string is needed when we make our diagram for our pattern? So what do we mean? Well, so right now, we've marked our throws, and we're going to put down our arcs. In this case, we'll use some string here. So let's start with the 3. So we'll grab our piece of string, and we'll loop it on to one end, and then we're going to go 3 beats. So that means it's going to land over there, and now we have it. Okay, so there's our 3. Next is a 0. Well, that's really easy. No string is needed. Or, as you might say, no strings attached. All right, how about the 9? Okay, well, that's going to be really long. A lot of string here because it's a big number. The bigger the number, the more string that you need. So if you look, it's a total of 6 beats. And since 9 is bigger than 6, it means we're actually going to wrap around more than once. So where are we going to end up? Oh, 1, 2, 3, 4, 5, 6. That's full all the way around. Then 7, 8, 9. So we're going to end up exactly opposite. So, okay, here we go. There's 6, and ending up exactly opposite brings us to there. All right, good. So that brings us up to this point. All right, that's a 5. Okay, so we need a bit of string here. All right, so where is the 5 going to land us? Well, 1, 2, 3, 4, 5. Not quite all the way around, but pretty close. All right, so we'll put our string here, and we'll go around. And let's hopefully we have enough. Oh, it's going to be tight, but that's okay. That's all right. We can make it. We can make it. There we go. There we go. Oh, yep, there. All right. Good. Whew. All right. 2. All right. Well, that's going to be pretty easy. Just 2 beats. Not a lot of string for that. It's going to be pretty short here. Okay, so we start, and we go 2, and we put it in. We've connected. All right. One last one. Another 5. Okay, so take our last piece of string here, and of course, if we go 5 around, that's 1, 2, 3, 4, 5. So we're going to end up all the way over there. And there we go. All right, good. All our string is in place. So these are our arcs. Now, our question, because we talked about this as a combinatorial proof, which means we're counting something, and we got to count in two different ways. So what we're counting is how much string do we need, and we want to count that in two different ways. So what's one way we can count? Well, one way we can count is we can say, look, this string that we need is based off of the throws. See, I needed a string of length 3, string of length 0, string of length 9, a 5, a 2, and 5. In general, if I want to know how much string I need, I add the lengths of the throws together. So we can say, all right, it's T1, the first throw, plus the second throw, all the way up to the last throw. That's the answer. That's how much string is needed. Okay, so that was one way to count it. Now we need a second way to count it. So what's our other perspective? Well, we can think about what's happening here and say, hey, look, at any point where I go around, how many pieces of string do we see? Well, it's 1, 2, 3, 4, and what these are the strings correspond to the balls. So for any piece here, between any 2 points, there's always going to be 4 pieces of string. It doesn't matter where we look, it's always 4 pieces of string. So always 4 pieces of string in each one of these intervals. In general, the number of pieces is the number of balls. We'll call that B for balls because we don't want to be too fancy. We want to make sure we understand. And then, of course, how many little intervals do we have? Well, it's the period which we use as n. So how much string did we use? We can say it's the number of balls times the period. Okay, so number of balls is B, and period is n. So these have to be equal. That's the idea of a combinatorial proof. And now, divide by n. And we come to the conclusion that says, aha, it must be the case that our number of balls is equal to the sum of the throws, T1 plus T2, plus so forth and so on. Divide that by n. So in other words, the number of balls is your average. Beautiful. Beautiful result. All right. Now, that says it's really easy then, if I'm given a pattern, how many balls do we need? So for instance here, if we add the numbers, 3 plus 0 plus 9 plus 5 plus 2 plus 5, well, that adds up to 24. The period is 6, because there are 6 numbers. 24 divided by 6 is 4. Now, there's a nice little result. And we should say it explicitly, even though, sometimes these results are so obvious, we're like, do we really need to say it? Yes, we really do. We really should say it. So we'll call it a little corollary. Now, some people say this word corollary, but I had, when I was a young undergraduate, back in the day, I had a professor from England, and spent a class explaining, no, it's not corollary, that's Americans. That's how they pronounce it. It's corollary, because you got to put the pronunciation, enunciate the right syllable. All right, so what's the corollary here? Well, the corollary says, look, if the average of throws is not a whole number, the pattern can't be juggled, right? Because it says, hey, when you look at the average, it's the number of balls. And so if the average is not a whole number, then that means you can't juggle it. It's not like, hey, if I have 2.5 as my average, I need 2.5 balls, right? Like 2 normal sized ball and like a medium ball. No. That's not what it means. It means, look, you can't juggle it. So if the average of throws is not a whole number, then it's not valid siteswap. Can't be juggled. All right. So it's good to write these facts down. Good to write these down. All right, so there we go. I really like this proof because it's one of those things that has this nice visual connection. And you see, like, oh yeah, I'm counting the number of lengths of string, and I can see it's like, oh yeah, it's those throws, and oh yeah, it's number of balls times n, and it just pops out beautifully. So great proof. But that doesn't mean that there aren't other good proofs out there, and let's talk about some other proofs. In particular, we're going to talk about one other proof. Our other proof, or if you like, our second proof, is going to use the notion of invariance. Now, when you see something like invariance, you can break it up. This first part, this in, just means not. And the variance, well, vary or changing. So not changing. So when we talk about using invariance, the idea is to say we really want to look at something where we have some part that we control which doesn't change even if we change something else. So in some sense, we're going to look at modifications of a large structure in such a way that we're not changing the thing that we really care about. And you might say, well, why do we do that? Isn't the easiest way to not change the part we care about is to not change anything at all? Well, okay, it's true that if we don't change anything at all, then nothing varies, but we don't gain anything. What we really want to do is we want to change things in such a way that things become easier. Now, you might say, well, that's kind of vague. What does easier mean? Well, easier really is saying something that's easy for us to understand. So in juggling, what's the easiest pattern? Well, the easiest pattern is the one where we always make the same consistent throw every time. So B, 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 dot, 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 B. So for example, for the 3 balls, 3, 3, 3, 3, 3, right? We know that pattern. We can just take a set of 3 balls and we can juggle it. And so now the question is, suppose you have that pattern, B, 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 B. How many balls do you need? Well, you can actually see the answer is you need B balls, right? Because you start throwing the first ball and you say, okay, well, I need another ball because the first ball hasn't landed. Okay. And then the third ball. Okay. And in fact, you have to keep throwing a new ball until you reach the point where you've gone B beats. At that point, after you've gone B beats, the first ball lands. All right. Now, great. I have a ball and I can just rethrow it. And the next beat, the next ball lands. Rethrow. And now you're good to go. So here, if we can get to that pattern, we know how many balls we need. So that's what our goal is to say, okay, can we think about modifying our pattern in such a way that in the end, we get down to this really easy pattern and we have the answer and life is good. All right, so the answer is yes, but how do we do it and how do we get there? Well, here's our goal. We're going to talk about manipulating our pattern, and in particular, we're going to focus on removing nestings. Well, what's a nesting? Here, we'll see it visually. We can even give an example with juggling. What happens is you have a very long throw followed by a very short throw immediately after, such that the second throw lands before the first throw. So the nesting says, aha, this throw, it starts and stops while that first ball is still in the air. So that's what we mean by nesting. So we want to get rid of that. Now, where does nesting occur? Do we have any simple patterns? In fact, there's a really simple ball, a 2-ball pattern, which looks like this. This is called the 1-3. It's a pretty simple pattern to juggle, but what happens is you have a very high throw and then a very quick throw across. So that really quick throw happens while the ball is up in the air. So that's the 1-3 pattern. And so you have that nesting of the short throw inside of the long throw. All right, so what can happen? Well, one thing that's true is if you think about it, we need to have the first throw be so large that the throw at this ith beat is bigger than or equal to the throw at I plus 1 plus a little more. Now, you might say, where's the plus 2 coming from? Well, notice here, between I and I plus 1, you have at least one beat, right? Well, not at least one, exactly one. Because we've gone from I to I plus 1, one beat. On the other hand, if we look at the landing time, well, this is at least one, possibly more. And so, if we think about the throws, see, the throw at beat I is measured by the distance from when we throw it to when it lands. And we say, aha, compared to the throw for I plus 1, it's at least 2, maybe more larger. Okay, so now, what's happening? Well, what we're going to do is we're going to say, okay, we're just going to switch. So what does that mean? Well, we're going to swap our landings. So we want that so that where the throw that originally came out at time I is going to land where the throw that came out at time I plus 1. And the throw at time I plus 1 is going to land at the time that was originally thrown at time I. Now, of course, we're just showing it in one piece, but we're going to do it all the way down simultaneously. So it's like we're taking a bunch of them. This is the nice thing about modular. We can say do it all simultaneously, and we're just going to swap. Okay, so what's happening to our throws? Well, in particular, we think about the length of time things are in the air. So what happens? Well, if I'm throwing at my original time at beat I, and I want to land here, well, what do I need to do? Well, let's just figure out the number of beats in between. There's one beat there, and t sub I plus 1 beats there. So that says the throw that we need to make is ti plus 1 more. All right, so that's what's happening to our throw here. Now, how about from I plus 1? Well, okay, what's that going to be? Well, if you think about it, what's happening here is it's like I'm starting from there, going to there. Okay, so I'm going in between. And the distance, well, it's this total length, but then I have to subtract 1. So that says the throw goes to ti minus 1. All right, now the key here. All other throws, modulo the period, are going to be unchanged. Since we're only dealing with just those two consecutive. So, all right, great. So, this is a beautiful fact. We're just saying, aha, lo and behold, we're just going to take these two consecutive throws, modify them a little bit, and we're going to say, let's see what happens. Now, one thing that you'll see is before we had a nesting, these will no longer nest. They're rigged to now cross. And so, in essence, we've reduced the number of nestings. And that's what's going to happen. You'll notice, of course, that if you look at this pattern, lots and lots of crossings, there's never a nesting. Nothing nests in this juggling pattern. So that's sort of the intuition about why we're doing this, is we're saying, hey, if I want to look like something without any nestings, I should start looking for places where I have a nesting and start throwing them out in some way. Now, what do we mean by saying we're using invariance? So we have to think about things. What's happening to these? And once we understand that, we can get a handle on what's going on. So let's start by asking ourselves the question, what doesn't change? So in other words, what's invariant? Well, first off, the total number of balls is not changing. because we're not adding balls, we're not removing balls, we're just rearranging where the balls get thrown and land. So we're not touching the total number of balls. And in fact, we should have added one other thing. We could say, what doesn't change? The fact that we're actually a juggleable pattern. So if we started with something that was juggleable, we're still juggleable because we are not going to create any new collisions. The same number of balls that landed at beat still land at that beat. Same number of balls thrown at a beat still get thrown at that beat. So we're still juggleable. Now, one other thing that doesn't change is the sum of all the throws. That one may not be so clear. So let's take a quick step back. So let's see what we have. Notice here, these two, when we add them together, it's going to be ti and ti plus 1. All right. If I add these two together, we'll have ti plus 1 plus 1, ti minus 1. The plus 1 and the minus 1 cancel, and the ti and the ti plus 1 will still sum to what they did before. And remember, no other throws got changed, so everything else still adds up as before. So that's why the sum of the throws is not changing. Okay, so we talked about what doesn't change, but what does change? We've already mentioned before we're removing nestings, but we're doing a little bit more. If you look at the throws, somehow you're bringing them closer together. What do we mean by that? Well, if you think about the picture before. So let's go back to the picture one more time, right? Because it's important to have this picture in mind when we talk about what's going on. So remember that the throw at ti was fairly large, larger than ti plus 1 plus 2, because we had that really long throw. So the really long throw is being reduced, and the short throw is getting bigger. So in other words, there was this sort of gap, and we're taking the top throw down by 1, the bottom throw up by 1. And so that they're moving them closer together. Doop, doop. And that's what we mean by things are sort of moving towards the center. So what's our general procedure? We have this idea that says, okay, we want to somehow move the throws closer together. So what we're going to do is we say, start with your pattern, and we look for a maximum height throw. Okay, great. And among all the maximum height throws, we find any one of them where the next throw that's made goes down. It's a smaller number. So, okay, you scan, and say, okay, here's the maximum height throw where the next number is smaller, which means there's a nesting. Now, it might be the case that all the throws are the same, in which case you can't find such a thing. So if you can't find anything, stop, but life is good. All the throws are the same. That's our B pattern. Okay, so if we're not in that, we scan for a maximum height where there's a smaller number right after it. If we find such a thing, okay, then apply that change. And so we say, all right, we got rid of that nesting, and now we have a new juggling pattern. Great. Repeat the process. And we scan, look for a maximum throw followed by a smaller throw. And repeat. Now, what's going to happen? Well, the first question you might say is, do we have to stop? In other words, can we get stuck in an infinite cycle where we keep going and going and going? And the answer is, we have to stop. Now, let's think about why. Because it's not a trivial thing. And so we have to be able to understand why, able to explain why. So here's sort of our reasoning. Because we're working with a maximum height throw, after we apply this operation where we remove that nesting, what will happen is that the maximum height throw that we had goes down. Now, that doesn't mean that the maximum height goes down, because there could be two throws at the maximum height, but at least one of the maximum height throws goes down. Which means eventually, if you apply this operation enough time, the maximum height does go down. And now we say, oh, well, what does that mean? Well, it means that if we were to keep going forever and ever, the maximum height would have to go down infinitely often, which means eventually we'd have to go negative. And you can't go negative. One of our basic assumptions is that we don't allow negative throws. And so that's why we have to stop. Because at some point, we can't keep going forever. There's this Latin phrase, reductio ad absurdum. It would be crazy if we could keep going forever. And so that means that, yes, we must stop somewhere. All right, so must we stop? Yes, because we can't keep going down forever and ever. Now, when we stop, what's the pattern? Well, the only way we can stop is if all the ball throws are at the maximum height. Okay, so what is that? Well, that says that if all the throws are the maximum height, that means all the throws are the same height. So when we stop, the pattern must be that pattern B, 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 you know. So it's that pattern that looks like B, 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 and it's a total of n times. Now, that's our stop. Now, you might say, okay, where did we start? Well, we started where we had T1, T2, all the way out to Tn. Okay, now here's where invariants come into play. What didn't change as we worked from one pattern at the start to the other pattern at the end? Well, what didn't change is that at every step, we made sure that the sum never changed, which means that this sum at the end, which is very easy to compute because I'm just adding the number b up n times. So, in other words, n times b has to be equal to this sum. Well, that's T1 plus T2 all the way up to plus Tn. Because that never changed. It didn't vary. It was invariant. Or, put another way, again, we can divide by n. We can say that the number of balls, that's T1 plus T2 all the way down to Tn over n. Again, same conclusion that we had. The number of balls is the average of the throws. All right. It's a really beautiful kind of proof because we're saying, okay, well, let's think about manipulation of our juggling pattern. And at the end of the day, what do we end up with? We end up with a really simple pattern that we can understand. And the thing that didn't change are the throws. All right. Well, probably it's good to see an example of what we mean. So here we go. We want to apply this procedure on a pattern, the pattern that we started with, 0, 9, 5, 2, 5, 3. So what we mean is we're going to come up with a series of juggling patterns where we're going to start at 1, and at every stage we're going to reduce a nesting. And it'll take a while for us to do this, but that's okay. By the time we get to the end, we'll be pretty confident. Okay, so let's write down, just so we know what's happening, we want to make sure that we follow the procedure. So it says the following. Suppose you have somewhere where you have a throw I and a throw I plus 1. And you have to have the following be true. This one is maximal, and this next throw is smaller than Ti. Okay? So that's what we're doing. We're scanning along, and because it's a periodic pattern, remember you can loop around. So in other words, it might be the case, that the 3 loop around back to 0. So if we see that, then what we do is we say, okay, that will go to, we don't change anything before the Ti, and then what happens is that we're going to get Ti plus 1 plus 1. So in other words, take this throw, add 1 to it, so switches, and then we're going to take that throw, and we're going to subtract 1 from it, and nothing changes after that. So that's what's happening in one step. All right, well, let's begin. So here we go. 0, 9, 5, 2, 5, 3. Well, we can see which one's the biggest number. It's that 9. So there we have that 9, 5. So what will happen here, we're going to have the 0, the 2, 5, 3. None of those change. It's only this pair that changes. So we're going to take this 5, and it goes up by 1, so that makes it a 6. And this 9 goes down by 1 to an 8, right? So this up by 1, that goes down by 1. All right, great. Next up, well, 8 followed by a 2. Okay, so what does that do? Well, okay, again, those are the only things that change. So the 2 goes up by 1, making that a 3. 8 goes down by 1, making it a 7. All right, well, now what? Well, largest number is a 7, 7, 5. Okay, so what happens? Well, here, the other numbers don't change. So we have 0, 6, 3, and 3. And what happens? Well, 7 goes down by 1, 6, 5 goes up by 1, 6. All right, good. Progress, progress. Now, we have choices. You see, there's 2 possibilities because there are 2 places where I have a maximum throw followed by a shorter throw, 6, 3, or that 6, 3. Now notice that 6, not a candidate. It is a maximum throw, but it's not followed by a shorter throw. So which one do we pick? And the answer is either one. In fact, we could, if we wanted to, and let's do it, we could sort of do a fork. Okay, so we'll start to fork here. So let's suppose we do our first one. So, okay, so we're going to have a 0, the 6, 6, 3 on the end. And now we'll do a swap, right? So it'll be a 4, 5, right? Because that's going to go down by 1, that goes up by 1. Okay, well here, well, has to be the 6, 3. Okay, so that does what? 0, 4, 5, 6. That doesn't change. But okay, up by 1, down by 1. Okay, so that's going to be 4, 5. All right, well now, 6, 4. Okay, so what is that going to be? Well, 0, 4, 5, and there's a 5 here. And now, okay, we go up by 1 with the 4, so that makes that a 5. Down by 1 with the 6, makes that a 5. All right, now where to? Well, where's a maximum throw followed by a shorter throw? If you look, see, I see 0, 4, 5, 5, 5. It's this 5 wrapping around. Okay, so that's all right. We're allowed to wrap around because it's periodic. So wrapping around, perfectly fine. So what will that give us? Well, okay, so this middle part doesn't change. That 4, 5, 5, 5. So what's going to happen is that this 5 is going to go over to there, and it's going to become a 4. All right. And then this 0 is going to come to there as a 1. Okay, good. Great. Now, where to from here? Well, we can see there's a change right there. So, what will happen? Well, that'll be a 4, 4, 5, 5. These parts don't change. And then we say, okay, look, this 1 will become a 2, and the 5 will become a 4. All right. Well, then there's the 5, 2. Okay. So 4, 4, 5, and a 4 on the end. But now we swap, right? So 5 goes down by 1, makes that a 4. 2 goes up by 1, makes that a 3. And finally, the 5, 3. Okay. Well, the 4, 4, the 4, 4, 5 down by 1, 4, 3 up by 1, 4. And we have to stop, because we never see this type of occurrence again, where a large throw followed by a small throw. Aha! Success! Now, you'll notice along the way, these are all different juggling patterns. In fact, they're all distinct. And one thing you could say is, well, how do we know that? In essence, one thing that you can think of is we've changed the number of nestings at every stage. And so they all have different nesting counts. So they have to be different patterns. Now that's a little bit more subtle. We'll get into nestings and crossings later on. So in the pattern of figuring out, hey, how many balls do I need to juggle this? And the answer is 4. We say, well, look, this one pattern, we saw, how many do we see? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 intermediate patterns. All of those are new patterns that we can now try to juggle. Or we can have somebody else try to juggle for us. Now, we're not done. Well, we are done in the sense that we ran it, but we said, hey, it forks. And we ran it where we said, let's change this one. But we could have changed that one too. All right. Well, what would happen? Well, we would have 0, 6, 3, 6, and then 4, 5. All right. And now what? Well, and now we can say, well, where's a maximum throw followed by a shorter throw? And we see, hey, there's 2 candidates. So, well, we can pick one, right? All right. Well, let's suppose we pick the second one. Well, so if we did that, 0, 6, 3, then the 6, 4 would go to 5, 5, and then we have 0, 6, 3, 5, 5, 5. All right. Well, now what? All right. Well, 0, 6, 3, 5, 5, 5. There's the place where we can change. Okay, so we carry it out. That would make it a 0, 4, 5, 5, 5, and a 5. Okay, so 0, 4, 5, 5, 5, 5, 5. Have we seen that before? Yes, it's right there. And so, lo and behold, we can just now follow that chain through. Okay, great. So we know it works. But we still have one other thing we could have tried, which is, we could have forked here. Wow. Okay, well, let's follow that path. See, all of these are different patterns that we're discovering here. So, if we follow that path along, what would we have? Well, we would have 0, and then we would have a 6, 3 would become a 4, 5, 6, 4, 5. And then the 6, 4, 5, the 6, 4, that has to be the one that changes. Okay, so that becomes 0, 4, 5, 5, 5. And one more 5. And we're now like, aha, again, back to work. And then we can do it. Good, good. So now, look at all these different patterns. So many. But that's the procedure. So there's how you can always figure out number of balls. Run the procedure until you get everything the same. Whatever that number is, that's the number of balls. All right, good. Keep practicing. See you again.